Thank you, Gabriela, for this introduction. Well, so my work in the project Prometeo is experimental physics. So I'm attacking experimentally the issues that my collaborators work in the theoretical front. So we are mostly working on physics beyond the standard model, and standard model for us particle physicists is a model, a theoretical model, very well tested so far, that unifies most but not all of the interactions in nature. So we have particles that are matter particles, and particles that are responsible for the interaction between those matter particles. What we want to do in this project is to extend this model, the standard model, to other theoretical scenarios, because there are some shortcomings, some problems, some issues that we have to attack. Within this model, supersymmetry is what I'm working on. Supersymmetry is an extension of the standard model that proposes a symmetry between these matter particles and the interaction particles. So there are many more particles that are introduced in the symmetry in nature, and we have and these particles can be produced in the collisions of particles in colliders. In this respect, I work in 2 experiments of the Large Hadron Collider. This is the most powerful accelerator so far in particle physics. It is situated at CERN, near Geneva in Switzerland. And I work in 2 particles, two experiments mostly. So Atlas experiment, a very big experiment, and a smaller one, MEDAL. So I said a few words about supersymmetry. So supersymmetry wants to solve some problems like the problem of the dark matter. So we know that in the universe we have observed that there is much more gravitationally, there is much more mass than we can see visible through the stars, for instance. And there is no way in the standard model so far to account for this lost, let's say, mass. Supersymmetry naturally introduces this kind of particle that could be possibly the solution to this problem. Beyond that, it also has other, gives solution to other problems, like the problem of the Higgs mass. So within the standard model, the proposed Higgs mass is not really that low as it has been observed so far. It can be extremely higher. Why is it the one that we observe and we have discovered rather recently, a few years ago, at CERN? Supersymmetry is one of the theories that really gives a solution to this problem. This is why we search for supersymmetry. Beyond supersymmetry, there is also other theoretical scenarios that we search for in experiments. One of them is Atlas, which is one of the biggest experiments in the LHC, but there is a smaller one, MEDAL, which is specialized for particles that live long-lived, they're long-lived, and they are massive, extremely massive. And apart from supersymmetric particles of this sort, it is also dedicated to the detection of magnetic monopoles. This is a proposal that extends the existing symmetry of the electrodynamics as we know it. So everybody knows that electric charge can be found in nature, while we don't have only north or south pole of a magnet. So magnetic monopoles are objects that precisely they give this symmetry between electricity and magnetism with this respect. So they have non-zero magnetic charge. And metal is really a leading experiment for these searches. And it also searches for supersymmetry.